Today I'm going to be doing for you a bunch of reactions that are parts of the types of reactions that we've studied already. These are found in your text, and what eventually I would aim for you to do is to find the chemical equation for the reaction that I'm going to do, write the equation into your notes, and balance the equation using some of the hints and techniques that are shown to you in the text and you may have already seen in some support material from either Mrs. Rudy or myself. I just want to show you the setup of the equipment and then we're going to get started. I'm going to lower this a little bit. My equipment is pretty simple to start with, but it's eventually going to look a little bit complicated. I'm going to start with a solution of pretty much water, but I've put a compound in here, Epsom salts, in low concentration. I need to put into the water some extra ions that will help with the reactions going to take place. And what I'm aiming to do is what we call the electrolysis of water. So we're going to try to break water apart, break the chemical bonds that are in it. And in order to do that, I have to pass an electric current through the water. You'll see that the solution has a little bit of a yellow color to it. This has been used before, has a little tiny bit of rust in it from the reactions that we've done. I'm going to pass electricity into this solution, and I'm going to do it by sending electricity down an electrode, and here you see a stainless steel electrode. Looks like the letter J. I'll bring it back a little bit. And I'm going to put this into two test tubes, and I'll apply an electric current to it from a source of electricity that allows current to only flow out of one terminal and go into the system, then eventually return to another terminal. You'll be able to see on this little power source that we have, which in effect is almost like a battery charger. There's two posts in here. I'm going to eventually put some wires onto those posts. Then we'll adjust the voltage so that it reads a value that's not too high, and we can then send electricity through the system. Now, in order to get the reaction to take place, I'm going to take two test tubes, which you've worked with already. I'm going to fill them with liquid, the liquid that we're going to be using in this big beaker. This gets a little bit messy at this point. I'm going to overfill the test tube just a little bit. I'm going to stick my finger on the top of it. A little squirt comes out. I'm going to lower the test tube into the solution down below. I'll do the same with the second test tube. Right to the top. Put my finger on this one. Flip it over, lower the test tube into the solution, and then I can clamp the test tubes up into position. And now, once they're in clamped positions, I'll be able to put the two stainless steel electrodes in. So let's make sure that's pretty tight. Yeah, that one's good. Let's try the other one. Okay, both test tubes are pretty firm. Then I'm going to take the electrode, which again looks like that J that I mentioned to you before. I'm going to put that down into the beaker so that it's able to come up underneath the test tube. Have to tilt that a little bit. Okay, so there's one electrode in position. The electrode is in the opening of the test tube down below. Let me bring that up a little closer for you. I'll do the same for the second electrode. And this one is going to be a little bit more difficult to do. Okay, so that electrode is up in position also. And then the next thing I want to do is I want to put the clips from my wires. We call these test leads. It's like a little alligator clip on a wire. I'm going to clip one electrode in position. Okay, so that's holding on. Whoops, that's holding on pretty good. I'll clip the other one over here. I'm trying not to let the electrode or the clips touch one another. Then we'll bring the wires over to the posts on the power supply, plug them in, and our setup is pretty much in good shape. It's good positions. And I'm going to bring it up just a little closer so you can see we've got the electrodes in there. They're clamped in position. I might have to do a little bit of adjustment in a little bit, but we're going to give this a try. Next thing I want to do is I want to push the power supply on and then turn up my voltage a bit. Also, I'm going to adjust the current. Now, this is pretty difficult for my computer to pick up visually, but I'm just going to bring it up a little closer. And in the test tubes themselves, there are bubbles that are forming. One of the set of bubbles is hydrogen. The other set of bubbles is oxygen. So we are literally using electricity to break water apart, break the covalent bond that holds the hydrogen and oxygen together, and it's working really good. Now that reaction is going to take a little while until I generate enough gas on the test tubes. And one of the things that I eventually want to check is what's the charge coming out of the power supply that's on this electrode, and then compare it to the charge that's on the other electrode. So I have a red and a black wire. I can compare what charges are coming out. Is it a plus or a minus? How's the flow of electricity going? And I also want to look eventually at how much gas gets trapped up in the top of the test tube. And we can do a little visual comparison once we get enough gas generated. Now, what I'm going to do, I'm going to let this reaction continue. I'm going to come back to it. So I'm going to pause the video at this point because I have some more experiments to show you. So in the meantime, this one can be reacting. We'll take a look at a couple other reactions, but we'll come back and finish up on this one. So here goes the pause. For the next reaction, I'm going to be showing you a double replacement reaction, and I'm going to be taking two solutions and putting them into a beaker. My beaker here is just filled with ordinary tap water, and then in two smaller beakers I have, in this case, some potassium iodide, and over here I have some lead nitrate, both of which are clear solutions. I'm going to use a barrel pipette to draw some of the liquids up and keep them separate from one another. And then what I'd like to do, and I'll try to bring this up closer for you, is show you what happens when we put them together. Let me move this out of the way. So we got both barrel pipettes, and we're going to take a couple of drops of each and drop them together into the water that's down below here. We want to see what's going to happen. A little bit of a squirt coming together. And immediately we've got a yellow color developing in the beaker. And this is very similar to a reaction that you guys did a while back where you were combining ions. When those two ions get together and mix, they form a new compound, actually 2 new compounds which are now in the water. One of the compounds doesn't dissolve very well, and that's a precipitate. That's the yellow material. The other compound is soluble. It's in the water, but it's not visible. It's one of those ions that you really can't see much of. So that's my second reaction, and I've got a little bit of material on the tip of the barrel pipette, so I'm not going to get this barrel pipette back into the beaker. That'll contaminate it. I'll just put this into the trash can. So that's the double replacement reaction, and these reactions, you're going to be able to find them in your text, and once you find them, my goal is to have you write down the equation that they're representing, and then also balance the atoms and ions that are in the equation and put that into your notebook. Now, I'm going to go back and look at the hydrolysis or the electrolysis of the water. So I'm going to go put us back on pause, see how that's coming on, and we'll come back and look at another reaction. Okay, the electrolysis reaction over on the table next to me here is still going on, so there's still bubbles being formed. We're still sending electric current through the beaker, but we'll eventually come back to that one. The third reaction I want to show you is a single replacement reaction, and the compounds that we're going to work with are a solution of copper nitrate, which has a nice blue color, and then a piece of zinc metal. Now, the piece of zinc metal, when I took it out of the container, was kind of gray, a little bit dull, and didn't have much of a shine on it. So what I did is I sanded one side of it, and you can see a little bit of a better color, or I'm sorry, better luster coming from it, and you can shine this up pretty well. But it does change over a period of time. So apparently over a period of time, this one has reacted with oxygen. But what we're going to do is we're going to take it and put it into the solution of copper nitrate over here. And not only is this reaction showing you what happens with a single replacement reaction, it's also showing you the arrangement of metals that react with certain substances, which we call the activity series. You're going to also be able to find this in your text. Certain metals are ranked very high, they're very active. Other metals are way down on the list of reactivity, and they react very slow. For example, gold and silver would be way at the bottom of the activity series of metals, and for that reason they are, around almost in the pure form. They haven't reacted too much, and it's also one of the reasons why we keep them as the metals which we use for jewelry, electrical contacts, materials that we don't want to have change over a period of time. But this metal is a little bit more active, so let's put it into our beaker. You've already seen the shiny side of the zinc. I'm going to just dip it into my copper solution, and I'm going to bring it up a little closer to the screen here. I'm going to take the piece of metal out, and I'll just hold it over the beaker here, but you can probably see now that the piece of metal has a coating on it, and it has become colored. Not too intense a color. If I left the piece of zinc in there a little bit longer, I would actually get a lot more material deposited on the surface of it. But the coating that we have is a coating of copper metal, a very, very thin film of it that has formed on the piece of the zinc. And that combination shows us that copper, when put together, zinc, when put together with a copper solution, is actually going to react pretty good. If I had some kind of a container made of zinc and I put a copper solution into it, over a period of time, the inside of the container would be coated with copper, and the zinc would be eventually dissolving a little bit. So